one of the exciting things about astronomy is that we have some beautiful things in our universe that we get to observe. And also from our first lab assignment, you learned about the scale of our universe and how it covers from the size of a proton to the size of the observable universe, many, many, many orders of magnitude, almost more than 40 orders of magnitude. So we're going to take a very brief tour of our universe and highlight some things that we're going to encounter this semester. So we're going to start by, imagine we're on the Earth and we leave the Earth's surface. The Hubble Space Telescope is this beautiful telescope right here. It's about the size of a school bus. I got to see a replica of it over Thanksgiving break of last year. The Hubble telescope is up in space above our planet, taking images of our universe. And the Hubble Space Telescope is sitting above the Earth's surface at a distance of about 5.6 times 10 to the 5 meters. And after you've completed your first lab assignment working with the mathematical tools that we use in astronomy, then you'll be able to understand these scientific notation distances as well. And so a little bit further than that, we have our moon, actually quite a bit further than that. We have our moon, and our moon is located at a distance from Earth of about 3.8 times 10 to the 8 meters. Our sun. Our sun is, of course, our nearest star. It is ours. And it's a distance of 1.5 times 10 to the 11 meters. We also call this special distance the astronomical unit. And we make a lot of comparisons between other objects in our solar system and in our universe to astronomical units, the distance between our Earth and our sun. And then Jupiter is located at a distance of about 7 times 10 to the 11 meters. But because of our orbits around the sun, sometimes Jupiter can be on the opposite side of the solar system compared to the Earth. And so the distance between our planets change over time as we're both orbiting around the sun and orbiting at different distances and different speeds. And so actually, our two planets could be as close to each other as about 4.2 AU astronomical units. So remember, that's the distance between the sun and the Earth. But they could be as much as about 6.2 astronomical units away from each other. And in this picture here, we have Jupiter with its beautiful banded structure. And we have at its poles, aurora. It has aurora, northern lights, just like our planet does too, just like the Earth does. And Jupiter also has 4 pretty large moons that we can see with our telescopes that we have here at Delta State. And those four large moons are called the Galilean moons because they were first seen through a telescope by Galileo. And again, we'll learn more about those this semester. Now, Pluto, much further away at a distance of about 5 times 10 to the 12 meters. This is a really recent image of Pluto. For a very long time, all that we could see through telescopes was kind of like a fuzzy dot of Pluto. But a spacecraft called New Horizons, this is what it looks like, went zipping out past Pluto and took this beautiful image of its surface. And now we know that Pluto actually has plains here. It's got craters, it's got mountains, it's got valleys. It has all of the geological features on its surface that we have here on the Earth too. And we'll find out that a lot of the planets in our solar system actually have similar geological features to our own Earth. And then we go much further away to the edge of our solar system called the Heliopause. That's at a distance of about 1.6 times 10 to the 13 meters away from our Earth. And so here we have a picture of the Heliopause. The Heliopause is essentially the edge of our sun's magnetic sphere of influence. So our sun is a magnetic star, it's creating magnetic fields, and those magnetic fields can fill up our entire solar system. And whenever you cross out of our solar system, cross this edge of the sun's magnetic sphere of influence, you cross something that we call the heliosheath, And then you're out into the interstellar medium, the ISM. And so here we have two spacecraft, Voyager 1 and Voyager 2. These spacecraft were launched from the Earth in the 70s, and they were just heading, they were launched with the idea to just let them explore our solar system, and they're continuing on throughout our solar system. And actually both of them have crossed the Heliopause, which is the boundary between the heliosphere and the interstellar medium, everything outside of our sun's magnetic sphere of influence, outside our solar system. And both of these spacecraft have already made it out of our solar system and past the boundary of the heliopause, the edge of the heliosphere. But this figure must be a little bit old because Voyager 2 even left our heliosphere in 2018. That's just our solar system. The nearest star to us is called Proxima Centauri. It's a small little star called a red dwarf. And Proxima Centauri, even though it's the nearest star to us, that distance is a distance approximately equal to 4.2 light years. 1 light year is the distance that light can travel in 1 year. And the cool thing about a light year is that 1 light year is the distance that light can travel in a year. And it also turns out to be that it takes light 1 year to travel 1 light year. So if something is 4.2 light years away from us in distance, we also know it took that light from that star to reach us. It took that light 4.2 years to get to us. The brightest star in our night sky is called Sirius, and it's located about twice the distance away from us as Proxima Centauri. Now, visible light is the light that we can see with our eyes. There's a whole range of light that we call the electromagnetic spectrum. And some parts of the electromagnetic spectrum, actually the majority of the electromagnetic spectrum, we cannot see with our eyes. And one part of that is radio waves. And radio signals, like TV signals or radio signals, travel as a radio wave. And these radio waves actually can leave the Earth's atmosphere. And so the furthest TV signal from the Earth has reached a distance of about 7.5 times 10 to the 17 meters. That's pretty far away. And so this TV signal comes from the 1936 Olympics in Berlin. That was the first time TV was broadcast over a long range. Just beyond that, we have something called the Romulan neutral zone at a distance of 1 times 10 to the 18 meters away from the Earth. If you're a Star Trek fan, then you'll know about the Romulan neutral zone. Other than that, it's fictional, so it won't be on an astronomy exam. Now, just a little bit further out from there, we have Kepler 16b at about 1.9 times 10 to the 18 meters. Kepler 16b is a really cool planet. So 16b, Kepler 16, that's the name of the star system. And Kepler is the name of the telescope that observed this star system, and B means that it's a planet. And so Kepler 16b is actually a binary star system. And we have 2 stars here that are orbiting each other. Imagine that you are on a planet like Tatooine in Star Wars, and you look up at that double star sunset. That's exactly what you might see if you were to stand on the surface of Kepler 16b. Although it turns out that the planet Kepler 16b is actually more like a gas giant, kind of like Saturn. So actually you couldn't really stand on the surface of that planet because that planet doesn't really have a rocky surface to stand on. But anyway, it's kind of cool to think about. Now Polaris, our pole star, is even further from there at a distance of 4 times 10 to the 18 meters away from us. Polaris will not always be the pole star, and it hasn't always been the pole star. And we'll talk more about that too. Cassieopeia A, a supernova remnant, explosion of a massive star at the end of its lifetime. This is one of my favorite space objects. These different colors indicate different temperatures of that material that's being blasted away from where that star center used to be, and also indicate that those materials are made up of different things. And we can use a technique called spectroscopy to sort out the different sorts of light that are coming from different parts of the supernova remnant, and that will tell us more about what that star and what the supernova remnant is made from. Now we get to things that are on the scale of our galaxy. Everything I've already mentioned lives inside our galaxy, which is called the Milky Way Galaxy. Here's a picture of what we think our Milky Way Galaxy looks like. And we're looking down at our galaxy from above. This is an artist's depiction. This bar right here is the center of our galaxy. And here's our sun. So our sun is actually located about halfway out from the center of our galaxy. So the galactic center is about 2.6 times 10 to the 20 meters away from our Earth and our solar system. But the edge of our Milky Way galaxy is about 2.4 times 10 to the 20 meters. So we, in fact, in our sun and our solar system, us orbiting around our star, we are located about halfway out from the galactic center. Now, the nearest galaxy to us is called the Andromeda Galaxy. Even though it's the nearest galaxy to us, it's still at a distance of 2.3 times 10 to the 22 meters away from us. And we just keep on going. You might have heard about the first picture we have ever gotten of a black hole. Now, that black hole, not inside our galaxy, not inside even the nearest galaxy to us, is located even further out than that, 5 times 10 to the 23 meters away from us. Here is a comparison of our solar system to the size of that black hole. So actually, the black hole is in the middle here. Our solar system could fit inside it. That's how big that black hole is. This ring of material around it is something that we call an accretion disk. It's material spinning around that black hole center. It's spinning around, it's getting really hot, and there's a lot of friction there, and so it glows. And so really with this picture of the black hole, the first picture of the black hole, we're not really seeing the black hole itself, because black holes essentially swallow up all the light that's nearby it. But instead what we see is this ring of material around the black hole, which indicates its presence. And this black hole is called the M87 Black Hole. It's located in the center of a galaxy called M87. And then beyond that, even further, we step back with our Hubble Space Telescope, and we can see so many other galaxies in our universe. We're only one of all of these billions of galaxies in our universe. And so this is what we call the Hubble Deep Field. It's taken by the Hubble Space Telescope, and we're looking, it's called the Deep Field because we're looking very, very, very far to the edges of our universe, and essentially looking back in time too. And we can see a bunch of different galaxies and stars in this image, and you can make out some of these are actually spiral-shaped galaxies in there too, like what the Andromeda Galaxy looks like and what we think our own galaxy looks like too. And so these objects, where all of these many different galaxies might reside, are located essentially at a distance of pretty close to 10 to the 26 meters away from us. And then we get to something called the cosmic microwave background, located at about 10 to the 26 meters away from us. The cosmic microwave background is a relic background radiation left over from the Big Bang, which is the spark that ignited our entire universe. We will get to the Big Bang and the creation of our universe at the very end of the semesters. We'll talk more about that then. And then finally, the edge of our observable universe, we expect to be around about 4 times 10 to the 26 meters away from us. And remember, the size of a proton is about 10 to the minus 15 meters. So that's 40 orders of magnitude from little proton to the edge of our observable universe. Everything that we know fits within 10 to the 26 meters. So our place in the universe, and by our place, I mean our location. We just went through a whole span of scales from our Earth to the edge of our observable universe. So if I were to ask you to come up with a cosmic address for where we live this is the flow chart that we would go through. So we start at our Earth. Our Earth is part of our solar system. Our solar system is part of the Milky Way Galaxy, and we talked about where we live inside our Milky Way Galaxy. And our galaxy is part of something called the local group. The local group is a local collection, local in our nearby area of our universe, a local collection of a few galaxies that are bound together by their mutual gravity. And then beyond our local group, we get to something called the Virgo supercluster. And the Virgo supercluster is a collection of more of these smaller collections of galaxies that are again held together by their mutual gravity. And there are multiple of these superclusters spread out throughout our entire universe. And it turns out that these clusters of galaxies are not necessarily spread out homogeneously in our universe. That means everywhere you look, you would see the same number of them. It turns out that galaxies like to sort of collect along certain streams or little regions in our universe. And there are other regions that are more void and empty. And that's something that astronomers are working hard to try to understand.